So the whole concept of chemical equilibrium is just to maintain a balance. If anything shifts or affects the equilibrium position, the reaction will react in such a way as to re-establish a new equilibrium position. Equilibrium meaning a state of balance, right? So the whole purpose of this topic is to return to a state of balance or to create a new state of balance, okay? So we've got chemical equilibrium. Now, I highly recommend that you memorize Le Chatelier's principle. It is asked in not every, but a lot of the chemical equilibrium past papers, and you get 2 marks for it. So it's basically like a free 2 marks, right? So I highly recommend memorizing Le Chatelier's principle. So Le Chatelier's principle states that a change in any of the factors that determine the equilibrium position of a system will cause the system to change in such a manner as to reduce or counteract the effect of the change. So what that means is whatever factor that is affecting or changing the equilibrium position of a reaction, that reaction is going to react in such a way as to return to a new state of balance or to counteract that increase or decrease or to counteract that change. For example, if you were to increase concentration, the reaction is going to react in such a way as to reduce that concentration that was increased. So that is a perfect example of that. Whatever you do or whatever factors affect that reaction, the reaction will react in such a way as to return back to its state of equilibrium. It's kind of like if you're walking on the street and for whatever reason you fall down. You're not then going to say, okay, because I'm now on the floor, this is my new state of being, I'm just going to crawl everywhere from now on. You're not going to do that, right? You're going to stand back up, dust yourself off, and then continue with your business. So same situation, this reaction is not going to remain or not going to continue to be affected by whatever is affecting it. It's going to return back to its original or back to a new state of equilibrium. So our factors that affect our equilibrium position is concentration, temperature, and pressure. Keep in mind that pressure is only for gases. We don't have pressure of liquids or solids. So concentration is for liquids, pressure is for gases. Then temperature can affect any type of substance. So let's have a look, or let us investigate concentration a bit, okay? So I'll move to the side and we can investigate concentration. So we've got concentration. Let's say we've got this reaction A plus B gives us C plus D. So for those of you that are confused on why we write the reaction symbol like that, it just means that this reaction can go either forward or backwards. It's a reversible reaction. If it is not a reversible reaction, it will be denoted by that arrow. But if it is a reversible reaction, the arrow will be moving forward and backwards. It's kind of like a split in a half arrow that's been reflected about the y-axis, okay? So we've got this reaction. Our reactants are A plus B. When they react together, they give us C and D. Now, let us assume that this reaction is in a state of equilibrium, right? Now, for whatever reason, some guy or some person went there and added more of A. So they've now increased the concentration of A. So that is the first thing that we are going to deal with. We are now increasing the concentration of A. How is our system now going to react to an increase in the concentration of A? So think about this, right? keep in mind, what is Le Chatelier's principle? Whatever is affecting the system is going to counteract that in order to return to a new state of equilibrium. So if we increase the concentration of A, won't our system now try to reduce the concentration of A, right? So our question was, if we were to increase the concentration of A within this reaction, how is this reaction going to now respond to counteract the increase in A, therefore returning the reaction to a new state of equilibrium? So let's have a look. If we increase A, it means we have extra A. So how do we get rid of the extra A? Is it not by favoring the forward reaction? Because the forward reaction will use up A. That's our goal, is to get rid of A, right? So if we favor the forward reaction, that is going to use up A, therefore getting rid of the extra A that was added. So how would we now write this in an exam? So we'd write it like this. Step number one, or before we even get to our steps, there's two important things that you always need to state whenever answering chemical equilibrium questions. You need to state which reaction is being favored. Is it the forward reaction or is it the reverse reaction? And second, you need to state the new equilibrium. You need to state whether our equilibrium position now shifts to the right or it now shifts to the left. Okay, those are the two important things that you need to state. So let us answer this particular question. We're first going to state that the forward reaction is going to be favored. So we are now favoring the forward reaction will be favored. Why are we favoring the forward reaction? Because that is the reaction that uses up the extra A that was added to the system. And secondly, we are going to state that the equilibrium position shifts to the right. Now, how do we know which direction our equilibrium position shifts? How do you know whether it shifts to the right or to the left? So if you favor the forward reaction, that means you're going from left to right. Therefore, equilibrium shifts to the right. If you are favoring the reverse reaction, that means that equilibrium shifts from right to left. So always keep that in mind. If you favor the forward reaction, equilibrium shifts right. If you favor the reverse reaction, equilibrium shifts left. An easy way to think about it is, if we are favoring the forward reaction, this is our reaction arrow. It's pointing right. That means equilibrium shifts right. If we were favoring the reverse reaction, our arrow would be left. Therefore, meaning equilibrium shifts to the left. Now, if this question was out of maybe like 4 marks or 3 marks, giving those two answers would not be sufficient to gain all the marks, right? So in addition to that, you can also discuss the concentrations of your reaction, of your reactants and your products. So let's have a look at A and B, right? How is the concentration of A and B being affected if our reaction favors the forward reaction? So our concentration of A and B will be reduced, meaning it will decrease, because if you favor the forward reaction, you are using up A and B in order to create more C and D. So you can state the concentration of A and B decreases, and the concentration of C and D increase. Okay, the reason C and D is increasing is because we are using up A and B to produce C and D. So basically what we've now done here by favoring the forward reaction is we are now using up A. Because we've increased A, we now need to reduce it. We now need to get rid of that extra that was added. So we use it up. Okay, now our system has returned to a new state of equilibrium. Let us change another factor. What if we decreased B? So let's have a look at a decrease in B. So that will be our question 2. We are now going to decrease the concentration of B. How will our system react if we were to decrease B? Keep in mind that if you decrease B, your system now needs to try and increase B. It needs to get more of B because B has been decreased. Think of it like if your body has a vitamin B deficiency, what is it going to do? It needs to now get more vitamin B, right? So you need to now go and have those vitamin tablets or supplements or whatever you're doing, right? So in this particular case, we've now decreased B. Our system needs to produce more of B to cover up for the decrease. So what are we going to do? We are going to favor the reverse reaction because that is the reaction that is going to produce more B to counteract the decrease in B. So we state the reverse reaction is being favored. Now, if we are favoring the reverse reaction, that means we are going from C and D to A and B. Our arrow is going to point left. So our equilibrium position is going to shift to the left. So we can then state our equilibrium position shifts left. Okay. Those are the two important pieces of information you always have to state. Which reaction is being favored and where your equilibrium position is shifting, right or left. In addition to that, you can also state the concentrations. So if we are favoring the reverse reaction, we then know that C and D is going to be used up to produce more A and B. We are trying to produce more A and B to counteract the decrease in A and B. So our concentration of A and B is going to increase, whereas our concentration of C and D will decrease. Okay. So that is how we would counteract, or how the system would counteract an increase in A or a decrease in B. Now let us have a look at the right-hand side of our equation. What if we were to increase one of the compounds or one of the substances on the right, or decrease one of the substances on the right? So for those of you who already understand this and are comfortable with this, please be patient. We'll get to a past paper question momentarily. I just want us to cover the theory so that everyone is on the same page and everyone is okay with what we are going to be doing within the past paper question. So we'll have a look at the theory related to concentration, the theory related to temperature, pressure, and our Kc values, okay? So let us investigate how our system would react if we were to increase C. So this will be point 3. If we increase C, what is now going to happen? So let's have a look at our equation. C is on the right side. If we increase our concentration of C, or if we increase the amount of product of C, how will our system react? So just as in point number 1, when we increased A, our system then tried to use up A in order to get rid of the extra A that was added. So it's going to be the same situation in C. If we increase C, our system is going to react such that it is going to try to get rid of the extra C, therefore favoring the reverse reaction, which means our equilibrium position will shift to the left. Why? Because we are trying to use up the C that was added. Okay. If you want to go a step further and discuss your concentrations, you can say that the concentration of C and D will decrease while the concentration of A and B will increase. Okay. Now, let us have a look at what would our system do if we try to decrease D, the amount of substance that we have in D, if we were to try to decrease that. Now, just as in B, when we try to decrease B, our system reacted in such a way as to try to make more of B to counteract the decrease in B. Now, it's going to be the exact same situation in D. If we decrease our substance D, our system will now try to produce more D in order to balance it out. So what our system will then do is it will favor the forward reaction, because that is the reaction that produces more of the D that was reduced or decreased. That means that our forward reaction will be favored, which then means our equilibrium position will shift to the right, and our concentration of A and B will decrease, and our concentration of C and D will increase. Okay, so that is concentration. Before we move on to temperature, does anyone have any questions relating to concentration? Anything that was not clear, something that you need me to explain, or a question that you have before we move on to temperature? Okay, so if everyone's okay, let us proceed to temperature. Now, when we are dealing with temperature down here, so temperature is another factor that can affect our Kc, or sorry, not our Kc, our chemical equilibrium. So temperature. Now, with temperature, you need to be familiar with what you've done last year. If you think back, you dealt with something called enthalpy, right? So enthalpy, also known as heat of reaction. In past paper questions, they don't really like to use the word enthalpy for whatever reason. They prefer to denote it as heat of reaction. Please take note that the heat of reaction is not the same thing as rate of reaction. It's two different things. Heat of reaction refers to enthalpy, this delta H. This is enthalpy, also known as heat of reaction. Now, if our heat of reaction, or if our enthalpy is positive, it means that the forward reaction is going to be endothermic. So let us put that in words. If our heat of reaction is greater than 0, it means that the forward reaction is going to be endothermic. For this, I would highly recommend that you memorize this, okay? Sometimes temperature can be the one that's kind of confusing. Concentration's a bit easier. Pressure is the easiest, but temperature is slightly confusing depending on how much you understand. So please just give me a moment. I saw that there was a message in the chat box. Okay, so I see C and D. Christabel, you want us to start again? Okay, let us quickly go back. I know I did not write C and D, so maybe it's easier if I write. So let me explain and write. So we'll come back to temperature in a moment. Let us quickly go back to concentration and finalize that. So I'm going to quickly go through A and B once more, and then I'll write down C and D. So let's have a look at A. If we were to increase the concentration of A, okay, if the concentration of A increased, how do we now, or how does our system now respond? Our system is going to try to reduce the amount of A. Think of it like if you asked someone for half a glass of water, but for whatever reason, that person comes with a full glass of water. So how do you get rid of that extra water? You can pour it down the drain, or you can quickly drink it up, right? But what's the main point behind what you are doing? You are trying to get rid of the extra, are you not? So if you have extra A, or if you have, let's say, for example, you've got now some extra money in your pocket and you see your friend's broke, you'll give him some, here, buddy, here's some cash there, you do what you need to, right? So if you have extra of something, the go-to is to give it away or to give it to someone that needs it or to get rid of it. If you have extra bricks and you're building a house and your house is done, now you see you've got 1,000 extra bricks. What do? You get rid of it. So it's the same situation. If you have extra A, the reaction is going to get rid of it. How does it get rid of it? It uses it up. So it's going to favor the reaction that uses up A. So if it's going to favor the forward reaction, because that is the reaction that uses up A and B to produce C and D. So because A was increased, you are getting rid of the extra by using it up. If you use up A, it means A is your reactants. That means the other one will be your products. So it goes from reactants to products, therefore going from left to right, therefore forward reaction. Okay. Now, if we were to decrease B, so let's say for whatever reason, you ask someone for a full cup of water and they only gave you half. So what do? You go back to the tap, you open it up, you put your additional amount of water and you're happy, right? If you order a shipment of bricks to build your house, and for whatever reason, the guy on the other side messed up. He only sent you 1,000, whereby you needed 10,000. Now you're short. How do you build your house? Do you only build one wall and then you say, okay, I'm done. This is my house? No, you go and you get the others. You need more bricks, so you go get more bricks. So the same situation will be here. If the system decreased B, or if you decreased B, or for whatever reason, the concentration of B decreased, the system is going to react in such a way as to gain more B so that it kind of balances out. You don't want more, you don't want less B. It's already been decreased. You want more B. So you need to see, okay, which reaction is going to give me more B? If I use my C and D as products, that will produce more A and B, and I want more A and B. So that's the correct way to do it. Now, the opposite, let's have a look at the opposite. If I say, okay, I'm going to use A and B as my reactants and C and D as my products, that means A and B is going to get used up, meaning it will decrease in order to get C and D. But we already had B decreased and we wanted to get more B. So is using up B to get more C and D the correct way to do it? No, it's not. We need more B. So we are going to use C and D as our reactants and B as the products. Keep this in mind. If A is increased, it's going to be the reactants because you want to use it up. If B is decreased, it's going to be the product because you want to make more of it. So whatever is increased becomes the reactant in order to reduce it. Whatever is reduced becomes the product because you want to make more of it. Okay, so keep that in mind. If something was increased, it becomes the reactant so you can get rid of it. If something is decreased, it becomes the product so you can make more of it. So I don't want to have to scroll up and down, so I'm just going to write a new equation, then we'll do C and D quickly. Okay, so that's our equation. We've got A plus B on the left, C and D on the right. Keep in mind, because it's reversible, you can say A plus B to produce C and D, or you can say C and D to produce A and B. But if the equation was written like this, That means you can only say A and B produces C and D. If the equation was written like this, you can only say C and D produces A and B. But because it's a reversible reaction, you can say either or. The left produces the right or the right produces the left. Products and reactants are constantly changing depending on your situation in a reversible reaction. Okay, so let us have a look at this. We need, or our question stated that C was increased. So if C is increased, we now need to get rid of that C. Remember what I said earlier? The one that's increased becomes the reactant, so you can get rid of it to produce something else. So C was increased, so we now need to get rid of it. What do? We know that because C is increased, it's going to become the reactant, which makes A and B the product. So our equation is going to go from right to left. So that is then going to become the reverse reaction will be favored. Now, if the reverse reaction is favored, that means that equilibrium position shifts to the left. So we've got equilibrium position shifts left. Now, if you want to be extra and add on some other stuff, you can discuss the concentrations. If our right-hand side is our reactant and our left-hand side is our product, our right-hand side is going to decrease. It's going to get used up to produce the left-hand side, to produce the product. So our concentration of our reactant, which is C and D, is going to get used up or decrease to produce more of A and B. So the concentration of A and B increase. Okay, now let us have a look at the last one. If we were to decrease D, so we decrease D. If we decrease D, that means our system now needs to produce more of it. So remember what I said earlier, if it decreases, it's going to become the product so that more of it is produced. So if D becomes the product, that means the left-hand side is the reactant. So we always go from reactant to product. So our equilibrium is going to go from left to right, which means we are favoring the forward reaction. So we'll say forward reaction will be favored. And our equilibrium position shifts to the right. Now, what can we discuss about the concentrations? So if we are favoring the forward reaction, it means that A and B are going to get used up to produce C and D. So that means the concentration of A and B will decrease. And the concentration of C and D increase. Okay, so that is concentration. So before we move on to temperature, before we get back to temperature, does anyone have any questions relating to this concentration that we've just discussed? Because I'm not going to come back once we go back to temperature. So if you have a question relating to concentration, please speak up now so we can address it before moving on. If you are shy and still typing out your message in the chat box, please raise your hand so I know I need to wait for you. If you are not feeling shy, you are welcome to unmute yourself and speak up. Okay, so let us proceed then. Let us get back to temperature. So what I was saying earlier with regard to temperature is that temperature is the second factor that affects our equilibrium position. Now, when we are dealing with temperature, it's important to know what enthalpy is. If you don't want to call it enthalpy, you can call it heat of reaction. Heat of reaction is the phrase that is used in your past papers. Most of the questions that you'll see with regard to heat of reaction is they'll ask you, does the heat of reaction affect this, or does the heat of reaction affect that? And it's a 1-mark question. You're usually just supposed to state increase, decrease, or remain the same. Now, please do not confuse rate of reaction with heat of reaction. They are two different things. Rate of reaction is the speed at which a reaction takes place. Heat of reaction is your enthalpy. That's the change in energy of your reaction, okay? So what is important to take note of when you are dealing with temperature is that a positive heat of reaction means that the forward reaction is endothermic. Please take note that that greater than 0 implies positive, okay? So I'll just put a little plus sign there. This means positive. Now, if our heat of reaction is negative, meaning it is less than 0, our forward reaction is then going to be exothermic. Okay, so there's two types. If our enthalpy is positive, our forward reaction is endothermic. If our heat of reaction is negative, our forward reaction is exothermic, which then means that the opposite or the reverse will be the opposite, okay? So if we have positive heat of reaction, that means our forward reaction is endothermic and our reverse reaction is exothermic. If our heat of reaction is negative, our forward reaction will be exothermic and our reverse reaction will be endothermic. Now, I would not recommend memorizing forward endo, reverse exo, forward exo, reverse endo. It's going to make you confused and it's easy to mess up like that. So what I would recommend is learn forward or learn positive endo, then negative exo. So think of it like this. Positive can be inside, you have your endoskeleton. Negative outside, exoskeleton. Maybe that's an easier way to think about it. So always remember, positive heat of reaction, forward reaction is endothermic. Negative heat of reaction, your forward reaction is exothermic. And then always remember the opposite. So just reverse will be the opposite, okay? So something else that's also important for you to take note of when you are dealing with temperature is that if the system increases temperature or if the temperature of the system were increased, it's going to favor the endothermic reaction. So think about this. If you increase the temperature in your system, right, that means that it's going to get hot. Think of it like, oof, it's a hot day, sun is busting, it's just hot. You need a drink, whatever situation is going on, it's just hot today. So what's going to happen is the reaction is going to be endothermic because that is the reaction that absorbs the heat energy. So think about it as though your body were to absorb all the heat energy around you. What's going to happen to the heat energy around you? It's going to get cold, right? It's going to cool down. So that's the exact same thing that's happening. Because the forward, or let's say because the temperature in this particular system was increased, it means that the temperature of that container or the temperature of that system is increased. It's hot. An endothermic reaction is a reaction that absorbs the energy from the surroundings. So it's going to absorb the energy or the heat from that system, and it's going to cool the system down. And a decrease in temperature favors the exothermic reaction. Why? Because an exothermic reaction releases heat into the surroundings. So if your surroundings are cold, if you then produce an exothermic reaction, the heat from that exothermic reaction will be spread out or released to the surroundings, thereby warming up the surroundings. Okay, so keep that in mind. Or alternatively, as students do best, you can just cram it. So, first piece of important information, if you increase the temperature, this is going to favor the endothermic reaction. If you decrease the temperature, that is then going to favor the exothermic reaction. Okay, so there's 4 important pieces of information in temperature. If it's positive heat of reaction, the forward reaction is endothermic. If it's negative heat of reaction, the forward reaction is exothermic. The opposite reaction or the reverse reaction would then be the opposite. Secondly, an increase in temperature favors the endothermic reaction, and a decrease in temperature favors the exothermic reaction. That is the most important things that you need to know and understand about temperature. So before we move on to temperature, is there anyone that has any questions? Because we're about to go into pressure. So if you say forward reaction is being favored, it's a shift to the right. Reverse reaction is being favored, it's a shift to the left. Can you please re-explain temperature? Okay, so let us do temperature once more, okay? Then we're moving on to pressure. So, excuse me, temperature. Let's start from heat of reaction once more. Heat of reaction, whenever heat of reaction is positive, the forward reaction is endothermic. So keep that in mind. Positive heat of reaction equals forward endothermic. Whenever the heat of reaction is less than 0, meaning that it is negative, the forward reaction is exothermic. So negative heat of reaction, forward reaction, exothermic. So hopefully everyone is okay with that part. Now, let us move on to the increase and decrease. If temperature increases, it means that the surrounding area is going to be hot. The temperature has increased, okay? It's hot right now. What reaction do we need? We've got 2 options. Do we need the reaction that's endothermic or the reaction that's exothermic? Let's have a look at what those 2 words mean. To be endothermic is when the reaction absorbs the heat energy, when it's endothermic, the reaction absorbs the heat energy from the surroundings. To be exothermic is when the reaction releases heat into the surroundings. So let's look at that. Let's start with exothermic. If our temperature has increased and we now favor the exothermic reaction, are we not releasing more hot air into the surroundings, making it even more hotter? So that's bad, right? We don't want to make it hotter. We want to cool it down. So let's look at endothermic. If we go with the endothermic reaction, if we favor the endothermic reaction, our surroundings is hot. The temperature's been increased. We're sweating now. So what do we want to do? Do we want the reaction that absorbs the heat energy, therefore making it cooler? Or do we want to release energy into the surroundings, making it hotter? We want to make it cooler, therefore absorbing the heat energy. So we are going to favor the endothermic reaction. So increase in temperature, endothermic. It's kind of linked if you notice. Let's have a look at this. We've got positive enthalpy, right? And we said positive enthalpy means what? Endothermic. Increase in temperature, is that not the same as saying positive? You're adding more. Endothermic. Can you see the correlation? Can you see how it's linked? Then let's have a look at the negative area. Negative heat of reaction. What does that mean? The forward reaction is exothermic. Negative can also mean to reduce, right? To reduce the temperature. So a reduce or a decrease in temperature favors what? The exothermic reaction. So it's all linked. All you need to understand is two things. Ask yourself something. If the surrounding is hot, do I want to add more heat or do I want to remove the heat? Obviously, if I'm feeling hot, I want to cool down. I want to get rid of that heat energy. So you go with the reaction that absorbs the heat energy, therefore cooling down the system. If the system is already cold, that means temperature has been reduced. We're now freezing out here. What do we want to do? We want to turn on the heater and introduce heat energy into the system. So what do? We favor the reaction that is going to release heat energy into the system. Which reaction is that? The exothermic reaction. So something important that you should have already noticed. If you don't know what words mean, you're going to struggle. Those key words on the side of the textbook that you always look at them and brush them off like, you're never going to use them. Well, now it's come to bite you. You need them. If you don't understand what a word means, how do you use it? So if you understand what endothermic and exothermic means, the rest is just common sense. You ask yourself, if I'm feeling hot, do I want to increase the temperature or decrease the temperature? And what type of reaction increases or decreases the temperature? That's all you're doing, okay? So I'll make a note of it for those that are not sure what the words mean. Endothermic, that reaction absorbs energy. And exothermic, it releases energy. Keep in mind, if you absorb energy, right? If you absorb energy, you're taking in all that hot energy and you're leaving behind cold energy. If you release energy, you're then releasing hot energy, making it hotter. Okay, so let us move on to pressure. Now, pressure is the third factor that affects our chemical equilibrium. It's also the easiest one. So, pressure. Now, when we're dealing with pressure, something important to take note of is that you are basically just looking at which side is bigger or which side is smaller. Okay, that's the general idea of what's going on when dealing with pressure. So let's say we've got this reaction, okay? We've got N2 plus 3H2, and that is going to give us ammonia. Okay, so keep in mind it has to be a balanced equation as well, okay? You can't work with an equation that's not balanced. So step number one, before you deal with pressure, balance your equation, okay? Now, we're dealing with pressure over here. So let's look at the left-hand side of our equation. If we were to add up the moles on the left-hand side of our equation, so keep in mind, if something doesn't have a number in front, it means it's 1. You know that x is just 1x, right? The 1 is just invisible. So same situation here. It's just 1 in front. Now, something else to take note of is that we are not adding these lowercase numbers, the numbers on the right. We're only adding the numbers in front of the substance or in front of the element. Those numbers on the right make use of whether, or not make use of, but notify or tell us whether it's a molecule or how many atoms of that specific substance there is. We are looking at the moles, so we want the numbers in front. Okay, so on the left, let's have a look at the left. What do we have? We've got 1 plus 3, which gives us 4 moles. That's the left side. Let's have a look at the right. On the right, we are only dealing with one substance, so we can just say 2 moles. Okay, That is step one is to balance your equation. Step two is to figure out how many moles do you have on the right and how many moles do you have on the left. Now, let's say we increase the pressure of our system, okay? So if we were to increase the pressure of this particular system, so we are now increasing pressure. What happens if we increase pressure? Keep in mind that if you increase the pressure, the system is then going to try to reduce that pressure. Okay, because always remember the system needs to return to a state of equilibrium. So if the pressure is increased, the system will try to decrease it. If the pressure has been decreased, the system will try to increase the pressure. So the system is always going to do the opposite of what was done. So now in this particular case, we have increased pressure. So our goal is to now reduce that pressure. Our system is going to reduce the pressure. How do we reduce that pressure? We reduce it by favoring the side with fewer moles. I'll repeat that once more. If you are decreasing it, you favor the side with fewer moles, the side with lesser moles. Reason being, if you are on the top and you want to come down, don't you go to a lower level? So if you have high pressure and you want to get to low pressure, don't you go to a lower level? So same situation. If pressure is increased, your reaction favors the side with fewer moles. If your pressure has been decreased, your reaction favors the side with greater moles. That's the only thing that's happening. So it's not that difficult, it's kind of straightforward. Increase in temperature, favor the side with lesser moles. Decrease in temperature, you favor the side with greater moles. So let's write that out. So we are now going to favor the forward reaction. Why? Because that is the reaction that moves to the lesser number of moles. Okay, now if we are favoring the forward reaction, where does our equilibrium position shift? Forward, so it's going right. Okay, always remember forward, right, reverse, left. So our equilibrium position shifts right. That's it. If you want to discuss concentration, you're welcome to do that, but depending on the mark allocation, you might not need to, okay? So, because we've already discussed the concentration part of it, I won't really discuss it. Now, let's move on to the next one. If we were to decrease temperature, sorry, pressure, not temperature. We are decreasing pressure. What is the system going to do? The system is going to try to increase the pressure. Okay, so how do we increase the pressure? We favor the reaction that moves to the greater number of moles. So which side has the greater number of moles? The right is 2, the left is 4. So we are going in reverse. We need to move to the left because that side has greater number of moles. So the reverse reaction will be favored. And what about our equilibrium position? Because we are moving in the reverse direction, our equilibrium position will shift left. Okay, so that's all that's happening. If the system's temperature, if the pressure of the system has been increased, the system will favor the reaction that moves to the lesser number of moles. If the pressure in the system has been decreased, the system will move to the side that has a greater number of moles. So let me write out those two notes for you so you don't forget. So Two things that you need to remember. Rule number one, if pressure increases, so if pressure increases, the system is going to favor the reaction that proceeds towards the fewer number of moles. You can say fewer or you can say lesser number of moles. And then if pressure is increased, the opposite would be true. So if we increase the pressure, or if pressure is increased, sorry, decreases, not increases. If pressure decreases, it's going to favor the reaction that proceeds towards the greater number of moles. That's it. Those are the rules that you need to remember. So we've covered concentration, we've covered temperature, and we've finally covered pressure. So those are the three factors that affect your chemical equilibrium position. Now, before we move on to discussing a catalyst, is there anyone that has any questions or something that we need to address before we proceed to a catalyst? Okay, so let us proceed. Let us discuss what a catalyst does and how does it affect our chemical equilibrium if it does. Now, what is a catalyst, first of all? So a catalyst is a substance that is added to a reaction, and that catalyst or that substance increases the rate of the reaction. Now, when a catalyst is added to a reaction that is already in an equilibrium, the forward reaction will increase, or the rate of the forward reaction will increase equally with the rate of the reverse reaction, which means forward equals reverse. If you add a catalyst, it's just going to increase the rate of the forward reaction at the same speed that it's increasing the rate of the reverse reaction. Now, a catalyst does not affect your equilibrium position. I'll repeat once more. A catalyst does not affect your equilibrium position. If you want to learn more about your catalyst, you can go back to your notes from rate of reaction. I think it was discussed in quite detail on what your catalyst is, the properties of a catalyst, what it does, all of that stuff. So in chemical equilibrium, the most important thing about a catalyst that you need to remember is that it does not affect chemical equilibrium position. This question can be asked in a 1-mark question, whereby they can state, if you add a catalyst to the system, will the equilibrium position shift to the right or to the left? Or they can ask you, will a catalyst affect the equilibrium position? And you need to say yes or no, or increase, decrease, or remain the same. So it's usually a 1-mark question. The most important thing to remember is that a catalyst does not affect equilibrium position. So let us move on to our last part of our theory before we get started with our past paper question. So we've got our Kc constant. Now this is extremely important. I would advise that you prioritize learning Kc over theory if you're in a situation whereby you don't understand anything and it's the night before the exam and you're completely blank, you have no idea what's going on. Learn Kc over your theory. The reason is because Kc is usually an 8 to 9 mark question. It can range between 7 to 9 marks, sometimes even 10 marks. Your theory part of your question is just about 3 to 5 marks. So there's more marks gained from your chemical equilibrium constant than from your theory. But in the best possible situation, you would have time to learn both. Okay. So let us discuss the chemical equilibrium constant. Now, if we have this equation A plus B that produces C and D, or if the reverse is true, C and D produces A and B. Those lowercase a and b's and c's and d's, what do those represent? Let's highlight them. This lowercase a, b, c, and d. If you think back to our pressure example, we had H2 plus, what was it? H2 plus, or rather N2, not H, sorry, was nitrogen plus hydrogen. So nitrogen plus hydrogen gives us ammonia. Okay. So in here, if you look at these numbers before your substances or before your compounds, that's what those A's and B's and C's represent, the lowercase ones. That's just the number that is in front of your element. And that number in front of your element becomes the exponent when you substitute it into your Kc equation. So if we were calculating Kc of this reaction of ammonia, we would have Kc equals our product. Remember, it's always product on top, reactant at the bottom. So we'll have NH3, it'll be the concentration of NH3 to the power 2 all over N2, the concentration of N2. Now, since N is to the power 1, we can leave it. And hydrogen to the power 3. So that is how you would represent your Kc equation for the formation of ammonia gas, okay? Now, let's discuss the equation. Those values that you substitute within the squared bracket, that is concentration, okay? Only substitute concentration in place of those squared brackets. Now, always remember, products on top, reactants at the bottom, okay? Now, a few other things that you need to remember about Kc is that Kc changes as temperature changes, meaning that Kc can increase with the temperature increase, or Kc can decrease with a temperature decrease, okay? So always keep that in mind. So I'll repeat it once more. Kc increases as temperature increases or decreases as temperature decreases. Kc changes with temperature. Now, when you are substituting into your Kc equation, you can only substitute gases and aqueous solutions. You cannot substitute liquids and solids. The Kc value of a liquid and a solid is a constant, so it won't really work out in our equation. So keep that in mind. The Kc equation will only accept gases and aqueous solutions. Okay, so there's two important notes. Kc changes as temperature changes, and only substitute gases and aqueous solutions. Now, what does it mean to have a high or low Kc value? So if you think about it from a mathematical perspective, okay, if you have a big denominator and a small numerator, so let's look at that. If we've got 10 in our numerator, sorry, the other way around. If you have a big numerator and a small denominator, so we'll substitute 10 in our numerator position and 2 in our denominator position. What is that going to give us? It's going to give us 5, right? Let's switch this around. Let's make it a small numerator and a big denominator. That is going to give us 1 over 5. If you put 1 over 5 into your calculator, you should get 0.2. So which is bigger, 0.2 or 5? It's the 5, right? So if we have a large Kc value, that means that our numerator was bigger than our denominator. what does our numerator represent? It represents our products, whereas our denominator represents our reactants. So if you have a big Kc value, it means your products were greater than your reactants. And if you have a small Kc value, it means that your reactants, which is your denominator, was greater than your products, which is your numerator. Okay, so keep that in mind. Big Kc value implies products greater than reactants. Small Kc value implies reactants greater than products. Okay, so this is a 2020 question, November question paper. Yes, Boipelo, you still have your hand up. Murendeni, what do you mean the catalyst theorem? I'm not sure what you're referring to. Okay, let us proceed. Now, this is a November 2020 exam paper. Let's see, we've got question 6. So let us read question 6. The dissociation of iodine molecules to iodine atoms is represented by the reaction taking place. Is a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is I2 dissociates into 2I. So something important, if you don't know what the difference between iodine molecules and iodine atoms, this will be slightly difficult for you. So let's take a step back and discuss the difference between a molecule and an atom. If you've got, let's represent our element by X. If you've got X2, that means there's 2 of X. You've got 2 atoms of X. That is a molecule. If you just have X, that is an atom. Remember, an atom is a single building block, whereas a molecule is 2 atoms together. So what is iodine molecules? Which is represented by iodine molecules and which is the iodine atoms? So if you look at I2, this is the molecule. If you look at I, that is the atom. Okay, the 2 in front of the I was just put there to balance out the equation. So let's read that above statement one more time. Oh, another key word is dissociation. Dissociation is one of the reactions that you covered last year. If you have A can break up into B plus C. Dissociation reaction is just to break something up into simpler compounds, okay, or substances. Now, the dissociation of iodine molecules to iodine atoms. So we have this iodine molecules that are now being broken up into simpler substances, namely being iodine atoms. Okay. Hello. So we've got the dissociation of iodine molecules to iodine atoms is a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is our iodine molecules on the left dissociate or break up to become iodine atoms on the right. Now, another important piece of information is the statement over here. Kc for the reaction at 727 degrees Celsius is 3.76 times 10 to the power negative 3. So this statement is extremely important. Keep in mind that if the temperature were to change, this Kc value would also change. Reason being is that Kc changes with temperature. Okay. Now, first question. Write down the meaning of the term reversible reaction. So a reversible reaction is one in which both the forward and the reverse reactions can take place. So we can go from iodine molecules to iodine atoms, and we can go from iodine atoms to iodine molecules. Both are, or both would, or can occur, that's a better word to use. Both reactions can occur, the forward and the reverse reaction. So reversible reaction is one in which both the forward and the reverse reactions can take place. Now, question 6.2. At equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. So there's two important pieces of information here. The pressure of the system is increased. So pressure is increasing. The next important piece of information is temperature is constant. So we know Kc value is going to remain the same for this change, but pressure is increasing. So if pressure increases, what would our system normally do? It's going to favor the reaction it's going to favor the reaction or move in the direction of fewer number of moles. So before we actually start with this question, let's write out our equation and let us discuss our number of moles on both sides. So our equation is I2 produces I, and you balance it out by putting the 2. Now, on our left, we've got 1 mole on the left. On the right, we've got 2 moles. So if our temperature was, sorry, not our temperature, if our pressure was increased, we now need to decrease pressure, right? So we're going to favor the reaction that tends to the lesser number of moles. So we would favor the reverse reaction, okay? So keep that in mind, it's important. Murendeni, you've got your hand up. Do you have a question? Okay, let us proceed then. So let's go back to our question. So our question stated, at equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. How will each of the following be affected? Choose from increases, decreases, or remains the same. So we've got 2 questions and we've got 3 options: increase, decrease, or remain the same. And each one of these is a 1-mark question. So we've got question 6.2.1, the value of the equilibrium constant. So do you remember previously I highlighted 2 important pieces of information? The second piece of information was constant temperature. And we know that our Kc increases or decreases depending on temperature. Kc changes as temperature changes. But if they've stated that temperature is constant, meaning it does not change, what will our chemical equilibrium constant be? It's going to remain the same as well, because temperature did not change. So let's write that down. Question 6.2.1. Kc remains the same. Reason being is that temperature is constant. And how does temperature affect our Kc? Kc changes as temperature changes. So if temperature does not change, that means Kc remained the same. So let's go back. Just give me a second. I see there is a question that popped up. Okay, cool. Now, question 6.2.2. The number of I2 molecules. So we need to find out How will an increase in pressure and a constant temperature affect the number of iodine molecules? So let's have a look. Our iodine molecules are on the left side, right? So we've previously stated, because pressure has increased, that means that our reverse reaction is going to be favored, because that is the reaction that tends to the fewer number of moles. So we are going to favor the reverse reaction. Now, if we favor the reverse reaction, are we not now producing more iodine molecules? Because we are using up the iodine atoms on the right to produce more iodine molecules on the left. Always remember, the direction that your arrow is pointing, that is the side that is going to produce more. More of that side is going to be formed. So here, it stated that pressure increased. So if pressure increases, we know our rule is whenever there's an increase in pressure, our reaction or our system is going to favor the reaction that tends towards the side with fewer number of moles, in this case being our reverse reaction. So we are favoring the reverse reaction, which means that the iodine atoms is decreasing and the iodine molecules is increasing. So in here, or for question 6.1.2, we are going to state increasing. And our reason is because, well, let us not put a reason for now, because I saw that we have to give a reason for this question in the next one. Let me double check. If I read wrong, then we'll come back and put a reason. Yeah, says explain 6.2.2. So we'll leave that for now. So question 6.3. Explain the answer to question 6.2.2 by referring to Le Chatelier's principle. So we've basically explained it verbally. Now let us write it down and put words to that. So this is question 6.3. We need to explain why we've stated that the amount of iodine molecules is increasing. Okay, just give me a moment. I see there is a question. May you please re-explain 6.2.1? Okay. 6.2.1, why does Kc remain the same? That comes from what we previously discussed in theory. Keep in mind that when we were discussing theory, we stated that Kc changes with temperature. So let us make a note of this. That way, when you have a look at this a bit later, you'll be reminded of that note. So the important note that will allow you to calculate or to determine the answer to question 6.2.1 is Kc changes as temperature changes. But let us go back to our question. What did our question state with regard to temperature? If you look at that highlighted part, constant temperature, that means that temperature did not change. So because temperature did not change, that means that our Kc value remains the same, because Kc changes as temperature changes. If temperature does not change, then Kc does not change. Okay. So let's go back to question 6.3. Question 6.3, we need to explain how we arrived at the answer in question 6.2.2. Why did we say increasing? Why did we state that the amount of iodine molecules is increasing? So first step, we can see that the pressure increased, right? We know that pressure was increased. Now, what does an increase in pressure result in? Keep in mind our rule. What did we say whenever there's an increase in pressure? We said that if pressure increases, the reaction or the system favors the reaction that proceeds towards the side with fewer number of moles. That was the explanation, or that was what we discussed when we were dealing with theory, right? So let us now answer this question. So we know that because pressure's increased, our reaction is going to favor the reverse reaction. So that's the first part that we can state. We can state to earn 1 mark, we can say that it is going to favor the reverse reaction. So the reverse reaction will be favored. That'll earn us 1 mark. Let us see how many marks is this thing out of. It's out of 2 marks. So let us add in 1 more note to obtain 1 more mark. So it is favoring the reverse reaction. And let me leave up that thing in blue. That'll earn us our 2nd mark. To state that if pressure increases, the reaction will proceed to the side that has fewer number of moles. So I'm going to leave it there. We'll earn 1 mark for the rule that we've written in blue and 1 mark for the yellow writing. Okay. So that's it. That is the reason that the number of iodine molecules increases, because our reaction favored the reverse reaction, thereby producing more iodine molecules. Now, let us move on to question 6.4. Question 6.4 states, at 227 degrees Celsius, the Kc value for the reaction above is 5.6 times 10 to the power negative 12. So as you can see, we originally started with 727 degrees Celsius. Now we are on 227 degrees Celsius. So the temperature has now decreased by 500 degrees Celsius. So a decrease in temperature results in a decrease in the Kc value. Please don't see 5.6 and 3.76 and assume it increased. Kc decreased, okay? If you want to prove that to yourself, take that 3.76 times 10 to the power negative 3 and subtract 5.6 times 10 to the power negative 12 on your calculator. You'll see that you end up with a positive value. If the second value, if that 5.6 was greater than the original Kc, you would end up with a negative value. So keep that in mind. Because the temperature decreased, the value of Kc also decreased. So question 6.4 states, at 227 degrees Celsius, the Kc value for the reaction above is 5.6 times 10 to the power negative 12. Is the forward reaction endothermic or exothermic? Fully explain the answer. So this is a temperature question. We now need to deal with temperature. So if you think back to temperature, let us actually go back to our temperature notes or our temperature theory and read through it once more, then come back to this question. So if you look at temperature, the two important notes that you needed to remember was that as temperature increases, the reaction favors the endothermic reaction, or the system favors the endothermic reaction. As temperature decreases, the exothermic reaction will be favored. So knowing that, let us move back to our question. So our question is the forward reaction endothermic or exothermic? So we need to state whether the reaction that goes from iodine molecules to iodine atoms, is that endothermic or exothermic? So let us write down our reaction and try to break it down and see what our answer is going to be. So our reaction is iodine atoms gives us iodine iodine molecules gives us iodine atoms. I'm using a forward reaction symbol only, not a reversible reaction, because they specified what is the forward reaction. So I want us to investigate that. So what do we know? We know that temperature decreased. Therefore, our Kc value also decreased, right? What else do we know? We know that previously our reverse reaction was favored. Why? Because there was an increase in pressure. So let us make a note of that, because we have to explain how we are arriving at our final answer. We don't know what the final answer is as yet. We're still trying to investigate and figure it out, right? So let us make a note as we go, so we know, or we can go back and review our notes to make a final conclusion. So we know that Kc decreased as temperature decreased. If Kc decreases, right? Remember, we've stated that a low Kc value indicates that the reactance is going to be greater than the products, right? So let's make a note of that. Because we have a low Kc value, it means the reactance is greater than the products, which means the reverse reaction is being favored. So let's make a note of that. The reverse reaction is being favored. Now, before we continue, let us go and see how many marks this was out of. It's out of 4 marks. So we can give 3 reasons and 1 final answer that can give us our 4 marks. Okay, so we've stated that because Kc, or because temperature decreased, that was a Kc decreased as a result of temperature, keeping in mind that Kc changes as temperature changes, right? And because the reactance is greater than the products, because keep in mind our Kc values has been reduced. Remember what we discussed in our theory, that if we have a low Kc value, it means that our reactance is greater than our products. So if your reactance is greater than your products, it means the reverse reaction is being favored, because the products is being used up to make reactants. It's going in reverse, right? So that is why we've stated that in blue. Now, next, what do we know? We know that because the reverse reaction is being favored, we can now conclude that the reverse reaction is what? It's exothermic, right? Why? Because temperature decreased. To go from iodine atoms to iodine molecules temperature decreased. Let's go back to the question. You can see once more that even in the question, it states that temperature decreased. We just needed to figure out, is it the forward reaction that's exothermic or the reverse reaction? Because what did we previously state? We previously mentioned that a decrease in temperature favors the exothermic reaction. Our job was to figure out which is the exothermic reaction. Which reaction is being favored? Is it the reverse reaction that's being favored or the forward reaction that's being favored? If the reverse reaction was being favored, the reverse reaction would be exothermic and the forward reaction would be endothermic. But if the forward reaction is being favored, the forward reaction would be exothermic and the reverse reaction would be endothermic. So depending on which reaction is being favored, that would allow us to then figure out which is the forward reaction. It would be the opposite, right? Now, we know that because temperature was decreased, a decrease in temperature favors the exothermic reaction. Why? Because it's now cold, temperature is being decreased. So what is the system going to do? It's going to favor the reaction that releases heat energy into the surroundings. That being the, that being the exothermic reaction. So let us write this down. The reverse reaction is exothermic. The only reason we were able to state that the reverse reaction is exothermic was because of our previous 2 points. We figured out which reaction is being favored. Is it the forward or the reverse? Okay, because it's the reverse reaction that's being favored, we can now state that the reverse reaction is exothermic. Now, our question wanted to know, what is the forward reaction? Is it endothermic or is it exothermic? Because we figured out that the reverse reaction is exothermic, the forward reaction is the opposite. So we can now conclude that the forward reaction is endothermic. Okay, so I saw that there was a message in the chat box. Please give me a moment to have a look at it. May you please start the explanation? Okay, let us redo question 6.4 from the start. Okay, so question 6.4, before we start with the explanation, let us read the question once more. Now, question 6.4 stated, at 227 degrees Celsius, the Kc value for the reaction above is 5.6 times 10 to the power negative 12, meaning that the Kc value has now decreased. Why? Because temperature decreased. So the next part states, is the forward reaction endothermic or is it exothermic? And fully explain your answer. So as you can see, it is a 4-mark question, which means you get 3 marks for explanation and 1 mark to conclude and say the forward reaction is exothermic or it's endothermic or whatever it is, okay? Okay, just give me a second. There is a question. May you please go back to the part that has the notes for the theory? There's something I didn't take down. I just want to screenshot. Okay, Minetle, I'll release the screenshots after the session, okay? So let us continue. Now, we need to figure out whether the forward reaction is exothermic or endothermic, okay? Whatever the, let's do this. Let's start by temperature, since that's already given to us. We know that there was a decrease in temperature, right? We know that whenever there is a decrease in temperature, we are going to favor the exothermic reaction. So we already know that the reaction that is being favored is exothermic, right? So we need to figure out, is the reaction that is being favored the forward reaction or the reverse reaction? If we are favoring the forward reaction, it means the forward reaction is exothermic. If we are favoring the reverse reaction, it means the reverse reaction is exothermic, therefore making the forward reaction endothermic. So I'll repeat that once more. Our goal is to figure out whether or not the forward reaction is endothermic or exothermic, right? Now we are starting at temperature because that is the information we were given. We were told that there is a temperature decrease. If you look at 727 and 227, you can see that it's decreased, right? To go from 700 to 200, that is a decrease in temperature. So temperature has decreased. So we ask ourselves this: is temperature a factor that affects our chemical equilibrium? Yes, it is. How does a decrease in temperature affect our chemical equilibrium? A decrease in temperature favors the exothermic reaction. Do you remember when we were discussing theory, I told you keep that in mind. We're going to use it later on. And as you've seen, we are now using it. So far, we made use of two of our factors that affect our chemical equilibrium. In question 6.2 and 6.3, we dealt with pressure. In question 6.4, we are now dealing with temperature. And in 6.5, we most likely will deal with concentration because it's a Kc calculation. We know that Kc involves concentration, right? So let's take a step back. We've now figured out that there's a decrease in temperature. And what is the rule? Whenever there's a decrease in temperature, it favors the exothermic reaction. So now we need to figure out which is the exothermic reaction, or we need to figure out which is the favored reaction, because the favored reaction is exothermic. So let's look at our Kc. We know that Kc decreased, right? Which means that because Kc decreased, it's a low value, which means that the reactance is greater than the products. Therefore, meaning that the reverse reaction is favored. If you don't want to think about it in terms of a big Kc value or small Kc value, you can think of it in terms of what we discussed in question 6.3. We are favoring the reverse reaction because pressure was increased. So pressure was increased, which means in order for us to return to a new state of equilibrium, we have to favor the reaction that moves towards the lesser number of moles, which is the reverse reaction. So whether you think about it in terms of a Kc value or in terms of pressure, you can see that the reverse reaction is being favored. So far we know that the reverse reaction is being favored, and we know that temperature has decreased. So how do we link a decrease in temperature and favoring the reverse reaction? So let's read our rules once more. We've previously stated that a decrease in temperature favors the exothermic reaction. And we've already discussed that the reverse reaction is being favored. If you want to think of it in terms of mathematics, let's do this. Our rule is if there's a decrease in temperature, the exothermic reaction is favored. So exothermic is equal to favored, right? We then know that based on our pressure and our Kc values, we've already stated that the reverse reaction was favored. So reverse equals favored. Think of it in terms of simultaneous equations. Favored equals favored. And what is that? It's exothermic, so we're substituting the left and we substitute the right. So does that not make the exothermic reaction the reverse reaction? So whether you want to think about it in terms of math, or if you want to remember your rules, that would be a more English perspective to think about it. It doesn't matter. As long as you can understand that the reverse reaction is being favored, and because there's a decrease in temperature, it means that the exothermic reaction is being favored. So if we connect those two, or if we link them together, what does that mean? It means that the exothermic reaction is the reverse reaction. And what was our question? Our question wanted to know which is the forward reaction. So we've already discussed that the reverse reaction is the exothermic reaction. So the forward reaction would be the opposite. If the exothermic reaction is the reverse reaction, our forward reaction will be the endothermic reaction. Our last question, question 6.5. A certain mass of iodine molecules is sealed in a 12.3 decameter cubed flask at a temperature of 727 degrees Celsius. Therefore, our Kc is equal to 3.76 times 10 to the power negative 3. So that one sentence has a lot of important information in it. So let's break down that one sentence. We've got this 12.3 decameters cubed, and we've got our Kc value from that one sentence. Decameters cubed, what unit of measurement is that? That is volume. Remember, anything cubed is volume, anything squared is area. So this is our volume. This is our Kc. So we now have volume and we now have Kc. If we continue to read, when equilibrium is reached, the concentration of the iodine atoms is found to be 4.79 times 10 to the power negative 3 moles per decameter cubed. So this is important. Now, moles per decameter cubed, what unit of measurement is that? That is concentration. So our concentration is 4.79 times 10 to the power negative 3 moles per decameter cubed. Now, which concentration is this? This is concentration at equilibrium. So keep that in mind. It's not any concentration, it's concentration at equilibrium. What do we need to calculate? So they say calculate the initial mass of the iodine molecules in the flask. So we are calculating mass initial, the initial mass of our iodine molecules. So let's start. How do we calculate initial mass? Let's start there. So this is question 6.5. Keep in mind that this question is out of 9 marks. You can see that the whole question is out of 18 marks, right? So it's 50% for theory, 50% for the Kc calculations. Most of the time, majority of your marks will be from Kc calculations, but in this particular case, they've split it in half. So let's see, question 6.5. We need to calculate the initial mass. So how do we calculate initial mass? We can use our formula, number of moles equals mass over molar mass. Because we are dealing with initial mass, we can make this the initial number of moles equals the initial mass over molar mass. Now, our molar mass of iodine is 254. So in place of molar mass, I'm now going to substitute 254. This can be found at the back of your question paper on your periodic table. Now, from here, we need to calculate the initial mass. So we're going to cross multiply. So our mass initial is therefore equal to the number of moles times 254. So we already have an equation that we are now going to use to calculate the initial mass. The only problem is that we don't have the initial number of moles. So this is now where we go and use our KC table in order to calculate the initial number of moles. So let us write down our KC table. You can do it here on the side. So in your KC table, the first is the initial number of moles. Initial in moles. Next, you have the change, and that is also in moles. Your change, another way of thinking about change is what is used or what is formed. And then you have at equilibrium. And that is also in moles. If you don't know this table, I recommend memorizing it. It's important. They're not going to give you the table in the question paper. You're going to need it. So concentration at equilibrium. Keep in mind that concentration is moles per decameter cubed. Okay, so this is now our table. Let's break it up. Okay, now what substances are we using? Before we continue with this, let's see. There are two hands that are up. Murendeni, Tay, and Tendai, you've got your hand up. What's going on?
Okay, say I was saying that you forgot to write the equation at top on the table.
Yes, I'm going to do that now.
Okay, so
Sharp. Then Murendeni and Tay, you have your hand. Okay, Tay, I see you sent a message. May you please go back to the previous slide? Okay, the previous slide is just basically our number of moles equals mass over molar mass equation. Now, because we are calculating the initial mass, I've now used initial number of moles. It's just a change in representation. It's still your exact same formula that you are used to, that you've been dealing with all the time. If you don't want to put the little I to remember that's initial, that's your business. It's completely fine. It doesn't really matter as long as you remember that that is the initial. Okay, that's all we're doing. Number of moles equals mass over molar mass. The only problem is that we do not have initial number of moles. So we need to calculate the initial number of moles from our table in order to then substitute it into this equation. So basically, we're using quite a simple equation. The only difficult part is that we don't have initial moles. That's how the difficult part comes into calculating that initial number of moles. Now, we've got our equation, right? That needs to go on top. Our reactants are on the left, our products are on the right. Depending on how many substances you have within your equation, that's how many columns you would have. So because we only have two substances, that being the iodine molecules and the iodine atoms, we are going to have two columns for our substances. Okay, if you had three substances, you'd have three columns. If you had four substances, you'd have four columns. But keep in mind, you only take into consideration what is in an aqueous state and what is in a gas state. If you have any solids, you ignore them. You do not include the solids within your KC table. So this is our equation. So on the left, we've got iodine molecules. On the right, we've got iodine atoms. Just give me a second to change this. This is wrong. This is supposed to be I, not I2. Atoms is I. So this is going to be our molecules on the left and our atoms on the right. The 2 that is in front of the I is just there to balance it out. Okay. Now, our initial moles, we do not know what that is. That is what we are now trying to calculate. So our initial moles, I'm going to keep it as N initial. That is what I am now calculating. Next, I've got my initial number of atoms. You cannot have an initial product. If you are baking a cake at the beginning, how many cakes do you have? You have 0, right? You cannot have a product at the beginning. You can never ever have an initial product. So that is going to be 0 always. Your product is always 0 initially. Now let's move on. Let's go back to our information to see what we are given so we can substitute it into our table. So from our question, let's see. Okay, something important that we've highlighted in green, we were given the concentration at equilibrium. Of what though? Let's see. When equilibrium is reached, the concentration of iodine atoms. So keep that in mind. That is the concentration at equilibrium of iodine atoms, not iodine molecules. So under the column of iodine atoms, we are going to substitute that 4.79 times 10 to the power negative 3. So at equilibrium, under iodine atoms, we have 4.79 times 10 to the power negative 3. So we've managed to fill in 3 values into our KC table. From here, let us see, what can we now do? If you remember, we were given a volume of 12.3. So our volume is 12.3 decameters cubed. Okay. So how can we now use volume with our concentration to calculate the number of moles at equilibrium? Because I want to calculate this value over here. So keep in mind this value is your number of moles at equilibrium. So let's calculate that. We have concentration and we have volume, so we can use our concentration formula of C equals N over V. Our concentration is 4.79 times 10 to the power negative 3. Our number of moles, that is unknown. That is what we are trying to calculate. Our volume is 12.3. Our number of moles at equilibrium is therefore going to be 4.79 times 10 to the power negative 3 times 12.3. And that then gives us 0.058917 moles. So here we can substitute 0, just give me a second, that looks weird. 0.0588917 moles. That is our number of moles at equilibrium. Now, we can then fill in this value next because we know how many moles was formed from 0. If we initially started with 0 and then at equilibrium we ended up with 0.058917, how many moles of iodine atoms were formed? It's 0.058917. Okay. Always your product section, the change is always going to be equal to at equilibrium, okay? Now something important. How are we now going to fill out the reactant section? How are we going to fill in the values of iodine molecules? Because we only have our iodine atoms column filled out. Now to do this, you can use change. This is only applicable in the change row. You can only do this with change, because keep in mind, change represents your equation, right? Change represents that balanced equation. And when you are dealing with a balanced equation, you can make use of mole ratio. So you can only use mole ratio in your change column. You cannot use mole ratio in at equilibrium or initial, or even concentration at equilibrium. That is incorrect. You can only use it in the change column. So if you look, we know that, let me just move it slightly up so that you can see the equation. We know that our iodine atoms has double, or is double, our iodine molecules. So if iodine atoms is double iodine molecules, doesn't that mean that the iodine molecules is half the iodine atoms? So in order for us to get the iodine molecules, all we need to do is take that 0.058917 and divide it by 2. So I'll write it out. 0.058917 divided by 2, because the mole ratio is 1:2. That is then going to give us 0.0294585. Let me just double check that. 0.294594585. Yes, that is correct. So that is the change, or that is the number of iodine molecules that's used to form the iodine atoms. That's 0.0294585. Now from there, how do we get our number of moles at equilibrium? We do that by subtracting the initial minus the change, and that gives us at equilibrium. So keep this formula in mind. It's the initial minus change that gives you at equilibrium. So if ever you want to calculate at equilibrium, it's always going to be initial minus change, and that will give you at equilibrium. So our initial is in initial minus our change, which is 0.0294585. So that is our at equilibrium. Because we don't know the initial, we just leave it in that form, okay? Now, in order for us to get our concentration at equilibrium, we can divide equilibrium, that n minus 0.029 so on, by 12. But that's still going to give us an equation with an unknown. Keep in mind, we already have Kc, right? So can't we just use our Kc value to find out what is our concentration at equilibrium? And in place of our number of moles at equilibrium, we can just substitute that n minus 0.02 and so on, and then solve for n. So let us do that. We are now going to calculate our concentration of iodine molecules at equilibrium. So we know that Kc is equal to the products, which is iodine atoms, and keep in mind it's squared over our iodine molecules. Iodine molecules is to the power 1. Why does our equation look like this? It is because iodine molecules gives you iodine atoms. This 2 here that is in front of that I, it's over there. This 1 that is in front of I2, it's up here. Now, let us go back and see what is our value of Kc. Our value of Kc is 3.76 times 10 to the power negative 3. So we substitute in place of Kc 3,76 times 10 to the power negative 3. Now, in place of I squared, we know that our value of I squared comes from our table. So let's have a look at our table. We calculated, or we were given, the concentration at equilibrium of iodine atoms as 4.79 times 10 to the power negative 3. So let us substitute that in. So 4.79 times 10 to the power negative 3 squared all over I2. We now need to find the concentration of I2. So to get the concentration of I2, we're going to say 4,79 times 10 to the power negative 3 squared all over 3,76 times 10 to the power negative 3. Now put this into your calculator. And that should give you the concentration of iodine molecules at equilibrium as equal to 6,102 times 10 to the power negative 3 moles per decameter cubed. Okay, so we have now found the concentration of iodine molecules at equilibrium. We know the volume, so we can now calculate the number of moles. So let's do just that. So we're going to use the equation C equals N over V. Our concentration was calculated as 6,102 times 10 to the power negative 3. Our volume was given as 12,3. Let us go and have a look. What is our number of moles at equilibrium? So our number of moles at equilibrium is N initial minus 0.0294589. So that is what we are now going to substitute in place of number of moles at equilibrium. So N initial minus 0.0294589, I think, or 85. Let's double check. 29458. 29458.5. Okay, so it's ending in 5. Now we can cross multiply, so we'll have 12,3 times 6,102 times 10 to the power negative 3. We can move this negative 0.02 to the left, making it positive 0.0294585 equals N initial. So our initial number of moles, once you put this into your calculator, let us see, 12.3 times 6.102 times 10 to the power negative 3 plus 0.0294585. That gives us a value of 0,1045 moles. So this is now our initial number of moles. All we did was calculate the concentration at equilibrium of our iodine molecules. Once we were able to calculate the concentration of our iodine molecules, we were then able to substitute that into our formula C equals N over V and solve for our unknown, which is our initial number of moles. From here, we can now go back to our original formula and substitute the initial number of moles. So as you can see, the table was only used to calculate the concentration at equilibrium. Once we were able to calculate the concentration at equilibrium using our Kc expression, we were then able to use our concentration formula to calculate the number of moles, whereby initial number of moles was one of the components of that number of moles. So let's go back to the original equation. Our original equation was initial number of moles times 254. So let us substitute. This is 0,1045 times 254. Therefore, our initial mass, once you put this into your calculator, gives you 26,54 grams. Always keep in mind that this is chemistry. You do not measure in kgs, you measure in grams. Now,